Hi, I'm Cameron White, Senior 3D Software Developer at Side Effects. In this video, we'll be looking in depth at how to deal with geometry for crowd agents, and in particular, having agents in the crowd use different combinations of shapes in order to have geometry variations. There are a lot of new features in Houdini 19 in this area for making the workflow of setting up geometry variations a lot simpler and also a lot more scalable for large crowds. So we'll be focusing a lot on the new tools that are available. We'll start off with an overview of some of the lower level basics, so how geometry is actually stored in the agent definition, and then how that geometry can then be assigned to an agent. So the agent definition has what's called the shape library, which is just a collection of geometry or shapes that are available for any instance of an agent to use. And each shape has a unique name to identify it. So you can think of this kind of like just having a bunch of packed primitives that all have a name attribute, and then agents can pick which ones they want to make use of. And this is actually basically how it's represented on disk. If you save out the agent definition to disk through, say, the agent definition cache swap, the shape library will just be saved out as a BGO file. And if you open up that BGO file, it's actually just stored each shape as a packed primitive with a name attribute with the name of the shape. One advanced feature to mention is that although the agent has a single shape library, when it's saved to disk, this can actually be split into multiple BGO files on disk and composed by including all of those shape libraries and combining them together. But we won't be diving into much detail on that in this video. So in order for an agent to use one of these shapes, you need more information than just what the name of the shape is that it should be displaying. If it's a shape that has skinning or blend shapes, we need to specify what deformer the agent should use with that shape. And this is something that's intentionally made separate from the shape itself so that you can mix and match deformers. So as an example, you might have some skin geometry that has facial blend shapes, but if your agents are all going to be in the background, you might not want to actually do any blend shape deformation. Instead, you might just want to do only linear skinning. And similarly, if you have a shape that just has normal skinning, you might want to have the option of using dual quaternion skinning or just normal linear skinning. So the deformer is kept separate from the shape and is sort of assigned along with it, rather than being intrinsically fixed as part of the shape itself. The shape's geometry, though, does need to have the attributes that the deformer is going to use. So as an example, the bone capture attribute has this capture weights that are used by the skinning deformers. So as I mentioned already, there's a few different deformers that are available by default. There's linear skinning, dual quaternion skinning, or blended linear and dual quaternion skinning, which is blended based on a point attribute, like what the joint deform swap exposes. And then there's also a blend shape deformer along with all the various combinations of blend shapes with skinning. So each agent's shape can only have just one deformer assigned to it, but that deformer can be composed of multiple deformers for something like blend shapes plus linear skinning. The viewport also has built-in support for these, so it can do linear skinning and blend shapes on the GPU for fast previews in the SOP viewport. If you have a custom deformer, it's also possible to implement that in the HDK if you want that custom deformer to be applied when the agents are rendered or unpacked. And finally, if you don't have a deformer that's attached to the shape, then we have what's called a static or a rigid shape binding. In this case, there isn't any deformation happening, but you also can then specify a joint in the rig that the shape should be attached to. So this is basically just parenting the shape to a joint, and it'll be transformed along with that joint in a rigid manner. So this gets us into layers, which are what we use to actually assign shapes to agents. So a layer is a set of shape bindings, and a shape binding is basically what I was just describing. So a shape binding has the name of the shape to use, what deformer to use, and if there isn't a deformer, what joint that shape should get attached to. It can also have a scale factor for the bounding box of the shape, which is something that we'll talk about in a bit more detail later. So since the layer can have multiple shape bindings, this lets you assign multiple shape bindings together as a unit, but you don't necessarily have to do this. A layer could just have a single shape binding. The agent definition then has a list of layers that are available to use, and each of those layers has some unique name. And then when you're caching out the agent definition to disk, layers are stored just as a JSON text file with a list of the shape bindings. So once we have layers, to assign those layers to an agent and give it shape bindings that it should use, each individual layer has a list of layers from the agent definition that should be used to determine its geometry. So there's actually two lists of layers. One is the current layers, which are the shape bindings that are going to be displayed in the viewport or when rendering or unpacking the agent. And then there's also a list of collision layers, which are defining what geometry should be used for things like the collision geometry in the bullet solver for ragdolls, and also for things like computing the bounding box of an agent. This is where there was a pretty significant change in Houdini 19. So previously, each agent could only have a single current layer or collision layer assigned to it. So that one layer had to contain all of the shape bindings that the agent should be displaying. So this meant that if you want to have a lot of random combinations of shapes throughout the crowd to make variations, you had to create a separate unique layer for every unique combination of shapes. So this quickly results in a pretty large number of layers being created, which could present a lot of workflow problems. The other problem was that if you wanted to create a new layer, that involves adding it to the agent definition. And this is a problem if you have a workflow where you first build and cache out the agent definition to disk, and then you load that separately into a bunch of shots for the artist to work on. So if the artist working on a shot wanted to set up a new combination of shapes, they couldn't actually just do that on the fly. They had to go back and modify the agent definition. So this often turned into a workflow where you'd have to just maybe pre-generate a large number of all the possible combinations of shapes that you might come up with, which again produces a really large number of layers. And then the artist just picks and chooses which layer combinations that they want to use in the shot. So now with the ability to assign multiple layers to an agent, this actually has a really big change to the workflow. So instead of having to create a layer for every unique combination of shapes, instead you can just assign multiple layers to an agent to produce the combination of shape bindings that you want. So downstream, an artist can make new combinations on the fly just by assigning a different set of layers to the agent, and they don't have to go back and modify the agent definition. So with this workflow, instead of having a really large number of shape bindings in each layer, you can just have a relatively small number of shape bindings per layer. So it could just be a single shape binding if you want to be able to just individually assign a shape to an agent, but it might also have multiple shape bindings if there's a set of shapes that you want to be able to easily assign together as a group. So an example of this would be, say you have a pair of shoes that are two individual shapes, but you always want to be assigning those two shapes together as a unit. So it's up to you how you want to organize things to make it easier to build up the geometry variations. But the end effect of this is that you can just set up a fairly small number of layers while you're building the agent definition. So a layer for each set of shapes that you want to be able to mix and match to produce a final combination of shapes. And then downstream, the artist can just create whatever geometry variations they want by mixing and matching those layers and assigning them to an agent. So let's get into some examples now. So first we'll look at getting shapes imported into the agent definition and creating the layers. So there's a new 2.0 version of the agent layer SUP in Houdini 19, which has had a number of changes from the 1.0 version to work better with this new workflow, where we aren't going to be trying to create a single layer that has an entire combination of shapes to assign to the agent. Instead, we're trying to create smaller layers that we can mix and match together to produce the final set of shape bindings that should be assigned to an agent. First, just as a review, we'll look at the 1.0 version of the agent layer SUP, which I have here. So this was very much based around creating just a single layer at a time, and that layer had the full set of shapes that should be assigned to an agent. So here we're just creating a single layer, so we're specifying the layer name. You can optionally copy from the source layer all of the shape bindings if you wanted to, say, take a layer and add a couple more shapes to it. And then the multiparm here was the main way of adding shape bindings, where just one by one you either attach a shape binding from some shape that already exists in the agent definition, or manually adding a shape by pointing it at some SOP geometry somewhere. And then there was an option for adding a bunch of shapes at once through the second input. So this was a little bit more procedural, but it was still very much based around just adding all of those shapes into a single layer. So let's look at the 2.0 version of the agent layer SUP. So I'll just drop down an instance of that and wire it into my agent here. So the first part of this node is just adding shapes into the shape library. So kind of like the second input that was on the agent layer 1.0 SUP, we'll use the second input to add all of our shape geometry. So I'll just wire this into our geometry here, and I've just set up a simple test character to work with. So this is based off our mocap biped 3 character, and then I've just done a little edit to the geometry to create some interesting shape variations to work with different visual colors, just to make it easy to see what's happening on the video recording. So here we've got our shape geometry, which has a couple different variations of pants, shirts, and shoes, as well as our base skin geometry. And we'll just be using this to show the basic workflow of setting up layers. So once I've wired the skin geometry in, the SOP will take that input geometry from the second input, and based on the attribute that we've specified here, so default is the name attribute, it'll basically just partition the geometry based on that name attribute and create a new agent shape in the shape library with the contents of each unique value of the name. So here we end up just having a bunch of new shapes added to the library with those names you saw earlier, like pants 1, pants 2, shoe L1, and so on. And then once we've imported all of those shapes, the next step is to actually create the layers that we want to have to group those shapes together and then be able to mix and match them when we're assigning those layers to agents. So there's a couple different ways to go about creating the layers. There's this multiparm here, and then there's also an attribute-based workflow as well. So I'll start off just showing the multiparm workflow here. So by default, there's one entry, and it's just set to create a new layer called layer 1, and it's going to add in all of the shapes that were just imported through the second input. And then this set current layers option here is set to star by default, so it'll set the agent to display all of the layers that were just created in this SOP. So if I turn that off, we'll see that the agent isn't displaying any geometry, and with it on, is just displaying this layer 1 layer that was created. So I'll get rid of this, and let's say we want to take our two separate shoe shapes, so like shoe L1 and shoe R1, and just make a layer combining those two shapes because we want to be able to assign a single layer to assign both of those shape bindings to an agent. So if we make a new layer called, say, shoes 1, then in the shapes parameter here, we can either specify a pattern like star or something like that, or just directly select which two shoes we want to add into this layer. The other option here too is rather than using the menu or just typing in shape names directly, you can also press this button to open up a tree view, which lets you more easily select multiple shapes if you're trying to add a whole bunch of shapes at once. And so then if we want to set up a similar layer for the other variation of the shoe geometry, we can set up one called shoes 2, and then we'll just add in the shoe L2 and shoe R2 shapes. And so if we want to see the layers that are being added, the set current layers option is by default displaying all of the new layers. So it's displaying both the shoe 1 and shoe 2 layers on top of each other. But if we want to see, a particular layer that we're working on as we're adding shapes to it, we can use this solo layer option, which will display only that layer and override whatever was set in the set current layers option. So this is really useful if you're adding a bunch of layers and you just want to see visually in the viewport which shapes are in that layer. And then in this collapsible folder, there's a few of the options that were available that you'll recognize from the agent layer 1.0 SOP. So there's an option to add in shape bindings from some existing layer that was already in the agent definition. And then you can also manually add shape bindings one by one with shapes that were already in the agent shape library if you need to do that. But the focus for this SOP is definitely on importing shapes and then immediately grouping those shapes into layers that are going to be assigned to the agent. Typically, with this workflow, an agent shape isn't going to be part of multiple layers as often as it was before, because instead of creating a whole bunch of layers for every combination of shapes, we're combining layers to produce the combinations. So that's the basic idea with the multiform-based workflow. And then the other option is to create layers based on an attribute on the input geometry. So just as an example, I'll replicate the same setup of adding the layers containing each pair of shoes. So on the input geometry, I'll just drop down a name SOP to create an attribute. And so if we call this attribute, say, my layer name, which is a primitive attribute on the geometry, which is empty by default, then if we want to, say, add the shoe L1 and shoe R1 shapes into this, and we'll call the value of this attribute shoes 1, and then I'll do the same thing for the L2 and R2 shapes. So then on the agent layer SOP, if I turn on the layer name attribute option and set this to our my layer name attribute, what this will do is for every shape that was imported, the name of the shape, of course, comes from the name attribute because that's what the shape name attribute here was. Then it'll also look at the my layer name attribute, and then if that value wasn't empty, it'll create a layer with the name of that attribute value. So in this case, if we scroll down a bit, we'll see that our shoe L1 and shoe R1 shapes both have a value of shoes 1 for the layer name attribute. And so it'll create a layer called shoes 1 and add both of those shapes into it. So if we look here, we've got just a shoes 1 and shoes 2 layer, and we can individually view those if we want to. And these two options can be combined together as well. So if I wanted to manually add some additional shapes into one of these layers, like if I want to add into the shoes 2 layer, say the skin shape as well, you can mix and match these two workflows as you want to. So this attribute-based workflow can definitely be a little bit easier if you want to procedurally or more automatically set up how the shapes are grouped into layers. In this case, I was kind of just replicating the same manual workflow that I was doing. But depending on your assets that you're working with and how they're named, you might have a more automated way of assigning a layer name attribute based on what the name of the shape is, for example. One other useful trick to mention with this is that rather than creating a separate attribute for the layer name, you could also actually just set it to use the same name as the shape attribute. So if I set this to name instead, what this will actually do is create a layer for every single shape with the same name as that shape, and then that layer will just have that single shape in it. So you'll see here that now I just have a separate layer for every shape, and each layer just has a single shape binding. So this is a really useful shortcut if you're not actually trying to group the shapes together into layers, but rather you just want to have a single layer to be able to assign each shape directly to an agent without having it grouped together with any other shapes. So once we've actually created all the layers, then the next step is to finish building our agent definition as usual. And then once we've done that, after we populate the crowd, then we can assign those layers throughout the crowd to create geometry variations. So I'll just switch over to a different instance at the top here where I set things up correctly. So we have our shoes 1 and shoes 2 layer, which are combining the pairs of shoes. And then we have separate layers for the pants shapes, shirt shapes, and skin shapes. So if we go ahead and populate our crowd, then right now the agents just have whatever layers were assigned to them by the agent layer sub. So in this case, all of the layers that happen to get created. So you can see some of the overlapping duplicate geometry there. So in Houdini 19, there's a new SOP for assigning layers to agents, which is called the crowd assign layer SOP. And this is based around the new workflow of being able to assign multiple layers to an agent. So I'll first just clear out the current settings on the SOP. So there's a few options here at the top for what to do sort of at the start of the node before we start appending more layers to an agent. So the group parameter up here is just the group of agents to be operating on. So in this case, we're going to operate on all the agents in the crowd. And then you can control whether you're affecting the list of current layers that are assigned to an agent or the list of collision layers. And in this case, we're going to be working with the current display layers. And in the spreadsheet here, I've got the agent current layers intrinsic displayed just so we can see exactly what layers are being assigned to each agent. In this case, all of the layers are assigned to the agent because that's what the agent layer SOP left us with here based on the set current layers parameter. So the remove layers option here lets you remove layers from the list of assigned layers for each individual agent. So if I turn that on, it's set to star by default. So it's actually just clearing out the list of assigned layers. And so the agents are just left without any full visible geometry. But you can set this to whatever patterns you want. Like if I remove, everything except the skin geometry, for example, that just leaves us with the skin layer assigned to the agent. So this is useful if you want to sort of start from scratch and reassign layers from an empty slate, or if you just want to remove particular layers that were assigned to an agent. Kind of related to that is the switch layers option, which lets you replace one of the layers assigned to an agent with another layer. And this works a bit like the attribute string edit SOP. It supports the same kind of pattern matching. So one example here, just as a basic example, would be if we want to, say, replace the skin layer with the shirt 1 layer, for example. And this can be useful for something like swapping between a high LOD layer and a lower LOD layer or something like that. Or if you just have notes from a director of, this particular agent needs to have a different geometry variation, you can really easily do some quick swaps with this. So then next, once we've actually cleared away the layers, I'll just start from scratch here. Then we can go about using the main multiparm to append new layers to an agent. So if we turn this on, the default behavior here is just to randomly pick a layer. If we haven't specified any particular layer that we want to assign, it just randomly picks one so that you have something appearing. But the main workflow here would be to assign a random distribution of layers. So we could, for example, say, assign the shirt 1 layer to an agent or the shirt 2 layer, but we want to have, say, a lower weight for shirt 2 versus shirt 1 or something like that. So this lets you set up a weighted random distribution. If you want to specify a pattern of layers, you can also do that as well. So if, for example, I said we can either assign the shirt 2 layer or the pants 2 layer, this will randomly pick between these 2 layers with equal probability. So if I just renormalize the weights to make it really clear, there's an 80% chance that an agent will get a shirt 1 layer, and then there's a 20% chance that the agent will get one of these 2 layers, and then it'll pick between them with equal probability. So in this case, that ends up being a 10% chance of getting the shirt 2 layer or a 10% chance of getting the pants 2 layer. So you can use this to really easily randomize between different layers that are available and set up your own kind of custom weighted distribution. And then you can control the random seed here as well to control the random choices. So we'll reset this and just directly assign the skin layer as a starting point. And then we'll move on and append another layer. So in this case, we could, for example, randomly assign either of the shirt layers. We can, in this case, I don't really want to set up a complete weighted distribution, so I'll just do shirt star and randomly pick between the two with equal probability, and then just change the random seed a bit. And then so under this agents folder, you can also have control over which group of agents this layer assignment is actually being applied to. And this is a subset of the main group that the entire node is being applied to. So this can be really useful for building up more complex combinations of shapes. So as an example, if I want to, let's say I want to assign pants to the agents, but rather than just, assigning any random pair of pants to the agent, I might have some logic. If they have this shirt assigned to them, they can only have this pair of pants assigned to them or something like that. So what I can do here is I'll assign, say, the pants 1 layer to any agent that only already has a particular layer assigned to it. So the group parameter here is useful if you just want to directly select some group of agents to assign it to. But if I change it to selecting by current layer, this is done based on whatever layers the agent already has assigned to it. And this takes into account earlier multi-parm entries that assigned layers to the agent. So I can say, if the agent already has, say, the shirt 1 layer assigned to it, then it can have the pants 1 layer assigned to it. So this lets you build up more complex branching logic in terms of how the shape combinations can actually be created. And then finally, there's also an option to randomly cull the selection so that you only assign the layers to a certain subset of the agents. So I could say, I only want to actually assign this to, say, 50% of the agents, or maybe 100%, or whatever percentage you want. And then there's also a random seed to control this. So this can be really useful also for things like scattering props throughout a crowd, where you just want maybe 10% of the agents to be holding a sign or a flag or something like that. It's really easy for setting up these kind of random distributions. So that's the basic workflow here, is that we can just continue appending new layer assignments. And you can also split up this into multiple nodes, right? Because if I append a new instance of the crowd assign layers SOP, you can just continue appending more layers if it makes sense to split it across multiple nodes, just for making the setup easier to understand. Because the default behavior is that it doesn't replace the layers that the agent already has unless you obviously use this remove layers option or switch layers option. So I could take whatever layers the agent already had on the input and then append a new layer if I want them to now all have the shoe layers assigned. So you can continue appending new layers to the agent. You can also change the layer assignment at any time, right? So when I've been changing the layers that are assigned to the agent, I haven't been changing the pose or anything like that. So you can easily do this, post simulation too. If the simulation behavior looks okay, but then the director says, oh, this agent here needs to have some different geometry assigned to it, you can always replace what layers are assigned to an agent at any point in time. Going back to the agent layer SOP, there's a few more things to discuss. So one is how we can actually control the shape bindings that are being used for the layers. So by default, the agent layer SOP tries to figure out a reasonable default for what the shape binding options should be for each shape that's being imported through the second input. So you can control this through the shape bindings folder here. So the default behavior is that it'll try to figure out what shape deformer should be used based on what attributes and what the contents are of the input shape geometry. So in this case, for example, our input geometry is just a skin shape and it has a bone capture attribute, so it has skinning weights on it. And so the agent layer SOP will automatically assign a linear skinning deformer to it. And this works just as we'd expect. So if we play back some animation, we're seeing our skinning as we would want. But if you want to override this, there's a couple ways to do it. You can either directly set the shape deformer here, and this will apply to all of the shapes that are being imported. So we can set it to dual quaternion skinning, for example. And you'll notice we don't actually see an immediate effect in the viewport, and that's because the viewport only does linear skinning on the GPU. But if we append, say, an agent unpacked SOP, we'll notice that we can see a noticeable visual difference. So here, if we go forward a few frames, you'll notice that if we switch back to the linear skinning deformer, there is some different behavior there around the shoulders, for example. So setting the shape deformer here is one option, but also you can set it up on the input geometry and override it from an attribute. Similarly, you can also, for shapes that don't have a deformer, assign what transform name they should be attached to or parented to. So you can either pick from the joint here, or similarly, you can also set up an attribute on the input shape geometry for what joint that shape should be attached to. There's also an alternative way to set up or import rigidly bind shapes, and that's to use the kinetics-based workflow. So I'll show an example of that here. So in this case, what we're going to do is use the capture pack geometry SOP, which is the node in KineFX that we use for doing rigid captures. So what we're going to do here is take our agent primitive, use the agent animation on pack SOP, and just have it output the rest pose. And then here I've set up just a couple really simple props that are going to be bound to the hand. So here I've just set up a little tube with some color to make it visually distinctive. And I just positioned it roughly where I want to under the hand joint, and then similar for a box. And then here I'm using the merge pack SOP, which just merges the two shapes together, but packs them before merging, and then also assigns a name to each of them, which I've just configured here through these parameters. And then in the capture pack geometry SOP, all we want to do is take our skeleton geometry here for the agent, and then just decide which joints we want to capture each of these input shapes to. And so in this case, the joint that we want to attach to is just our wrist joint there. And then for the capture geometry, we want both of those shapes to be captured to this joint. So I just assigned it to star, but you could alternatively select those interactively in the viewport. And so if we look at the geometry spreadsheet, what this has done for us is we still have our packed geometry as we had set up on the input, but now we have a bone capture attribute that's describing rigid skinning, right? We just have a single joint that these points are weighted to, the hand joint, and it's assigned with a weight of 1. And so this is the format in KineFX that we use to represent rigidly skinned shapes, and the agent layer SOP will also recognize this. So on the input, when it sees that there's shape geometry that just contains a single pack primitive and its point just has a single weight, it'll recognize this as being rigidly skinned and import this as a static shape binding. So in this case here, I'm using the workflow we described before of just setting up one layer per shape. So using the layer name attribute set as the name. And then once we've populated our crowd, we can use the crowd assign layer SOP to randomly assign those two props throughout the crowd. So in this case, the tube and the box shape. And if we play this back, we'll see that those are being rigidly captured and following along with the transform of the wrist joint. So this approach can work a little bit better for setting up a bunch of props, since we can procedurally bind our shapes to the joints that we want to, and you can kind of reuse some tools that you'd already be using anyways in the KineFX toolset for setting up rigid captures and then importing those into the agent primitive. So one final thing to discuss for the agent layer SOP is how the bound scale option for a shape binding comes into play, and more generally, how the bounding box for an agent primitive is determined. So as an example, we're just going to turn on the primitive hole display option in the viewport, which just shows us the bounding box of the agent primitive so we can see what's going on. So the rules for computing a bounding box for an agent is that if the agent has a collision layer assigned to it, so in this case there isn't a collision layer, but it would prefer using the agent's collision layer to compute the bounding box. If there isn't a collision layer, it'll just use whatever the current layer of the agent is. And then it'll go through all of the layers assigned to the agent and merge together the bounding boxes from each of those shape bindings. So then for an individual shape binding, the way that the bounding box gets computed depends on what the deformer is. So if we have a rigid shape, the bounding box will just come directly from the shape itself because there's no deformation happening. And then the bounding box will get transformed based on whatever joint that shape is parented to. But if we have a skin shape, this gets a little more complicated because really the true bounding box of the skin shape is based on what the final deformed geometry is. But we don't usually want to actually compute what that deformed geometry is because that's quite expensive. And often we're also trying to use the bounding box as an optimization to avoid doing skinning in the first place, like detecting what agents are off screen based on their bounding box. So as an approximation, the bounding box for a skin shape is just based on the bounding box of all of the joints that are being referenced by the capture weights on the skin geometry. So in this case here, if we switch to the wireframe view, you'll see that this is why the bounding box isn't fully encompassing the skin geometry. Instead, it's just coming from the bounding box of all of the joints that are being used by the skinning. So this is where the bound scale option can be useful. So if we go to the shape bindings tab under the agent layer SOP, if we increase the bound scale, this ends up then inflating the bounding box of these shapes. And then similarly to what we were showing before with the shape deformer and transform name, you can also override this with an attribute on the input shape geometry. If you want to completely override the bound scale per shape, or alternatively, you can also just scale this based value based on an attribute. And then just as an example of how the collision layer and static shape workflow works, I'll just use the agent collision layer SOP as an example. So this SOP is a bit more intended for the ragdoll workflow, but I'll make use of it here. So here it's just setting up a new layer called collision, and it's assigning this to the agent as its current collision layer. So you can see here the agent collision layer, its intrinsic, is now just has a single layer assigned to it with this new layer that's been created. So I'll just quickly set up a couple of collision shapes for this. So here we'll just add a couple more shapes. And then you'll see now that the agent's bounding box is being computed from this collision layer, as long as that's been assigned. And then the bounding box is just computed by going through all of these rigid shapes and taking the union of their bounding boxes transformed by the joints that they're assigned to. So we'll see as the joints move around, the bounding box is following along with the bounding box of those rigid shapes. Now, the collision layer doesn't necessarily have to consist only of rigid shapes. It's just more of a convention since, of course, for something like ragdolls, you do want to have just a bunch of static shapes like capsules and boxes and so on. It's just that the collision layer is always preferred over the agent's current layer for computing bounding boxes, since typically the collision layer is a bit of a lower resolution geometry, usually consisting of static shapes that are quicker to compute the bounding box for. So finally, the agent Vellum and PackSop has had a few updates to make it easier to work with this new workflow of being able to have multiple layers assigned to an agent. So let's take a look at that. So just as a review, I'll first show what the workflow looked like in 18.5 using agent layer 1.0 and just assigning a single layer to an agent that has all of the shape bindings that it should be displaying. So here we'll just go through a little example file. So the basic idea with this workflow would be to start off with your agent primitive and import whatever your normal skinned geometry is for the agent. And then to set up your Vellum shapes, what you would do is use the agent on PackSop to get the rest geometry for the agent, and then proceed with doing your Vellum setup on this. And so here I've just got a couple different variations of a cloth shape to show the workflow around geometry variations with this. So here, the Vellum setup here doesn't really have anything crowd specific going on. We're just using the rest geometry shape from our agent. So here, I just got a basic cloth shape here, and then we're using Vellum constraints to configure it as cloth. In this case, setting up weld constraints between these two pieces of cloth just to demonstrate some different constraint types. And then finally doing some attachment constraints to attach it to the body. And then at this point, you could append, say, a Vellum solver if you wanted to just quickly test out the behavior on a single agent and make sure that your cloth isn't exploding or doing anything that you don't want. And then at the same time, I'm also over here just setting up another variation just to demonstrate the geometry variation workflow. But the workflow here is exactly the same of configuring it as cloth with the normal Vellum nodes and then setting up the attachment constraints. So then if we want to work with these Vellum shapes in the same way as any other shapes for our agent, so being able to assign them as layers and use the normal geometry variation workflows, we need to add these shapes into the agent definition. Now for Vellum, there's actually two pieces of geometry that are important, right? We have both the geometry for the cloth, but also the constraint geometry, so the first and second outputs here. And so what we'll use is the Vellum PackSop to pack and merge these two together. So in this case, we end up with two packed geometry primitives, one for the geometry output and one for the constraint output. And then we'll do the same over here for the other geometry variation. So then to add these shapes into the agent definition, we just use the agent layer SOP. So in this case, with this being agent layer 1.0, we're creating a single new layer, which has both the skin shape and then also the Vellum shape that we want to display along with it. So we're creating a new layer called skin and long cape. And then we're copying all of the shape bindings from the source layer, which is the skin geometry. And then we're just manually adding a single shape binding, pointing it at the output from the Vellum PackSop, and then assigning it a name. And then we repeat the exact same thing with the other Vellum variation. And so we end up with two separate layers for the combinations of Vellum shapes with the underlying skin geometry. But if we wanted to have different variations of the underlying skin geometry, we'd end up having to create a whole bunch more layers for all of those unique combinations. And then you go ahead with the rest of your agent definition setup as usual. There's nothing else special going on. And then when you populate your crowd, you could then assign those layers to agents in the same way you would with any other geometry variations. So here, I'm just using the crowd source SOPs options to assign just the normal skin layer to a few of the agents, and then for the rest of the agents, either giving them one of the two Vellum shape variations. You could also do the layer assignment post-simulation too, right? Because you can change the layers assigned to an agent at any time. So then just go ahead with the crowd sim as usual. In this case, it's configured to start as frame 20 because we're going to do a pre-roll a bit later on for our Vellum simulation. So there's nothing special really going on with the crowd sim here. And then once we have our simulated crowd motion that's been approved, you can go ahead and do the Vellum simulation. And so this is handled by the agent Vellum Unpacked which handles a bit of stuff for you with making sure that the constraints are updated for every instance of the agent, because the Vellum solver, of course, needs all of the combined geometry and constraints and collision geometry. And so we have to make sure that if there's, say, attachment constraints for our cloth, that for each instance of the agent, those attachment constraint copies are being rewired to reference the right unpacked agent. So we'll see that the collision geometry output here just has all of the unpacked polygons from our agents so that the Vellum solver can be colliding against them. So on the agent Vellum Unpacked there's a few options here. So first we get to select what agents we actually want to be unpacking. So you can either select by an explicit group, but more commonly you'll be selecting this based on what layer they have assigned to them. So in this case, the agents that don't have any Vellum shapes at all in their layer, we don't really want to be doing anything with them. So you'll see here that all of the agents like this guy here that didn't have any Vellum shapes aren't even being unpacked at all, and they aren't included in the collision geometry. So any agents that have one of the Vellum layers are being selected to unpack. And then the next thing is which shapes are actually going to be collision shapes versus Vellum shapes. And so this gets selected just based on the shape name here, because again, we only have one layer, so we need to pick from that layer which shape bindings are the Vellum shapes. So here we're just selecting, any of the cloth shapes are going to be our simulated shapes, and then anything else is going to be the collision geometry in our third output. And then finally, there's also some options here to set up a pre-roll, which can be really handy. So in this case, because our crowd simulation was starting on frame 20, we can set up a pre-roll so that our collision geometry blends from the initial rest geometry of the agent into the deformed pose from its first frame. So this can be a really convenient way to run a pre-roll. And then if you also want to use a particular pose, you can also specify a rest clip and sample time rather than just using the initial undeformed geometry. So once we've got all that, then we can just run the Vellum solver as normal and get our simulated cloth. So I'll just let that cook a little bit. And then finally, if we want to take our output from the Vellum solver, which is just our simulated polygons for the cloth, and display it along with the rest of our crowd, we just merge it together with the agents. But this has a bit of a problem here. So if we just took our original agent primitives and merged them together, we'd see that we still have all of the original unsimulated Vellum shapes that some of those agents had in their layers. And so what we actually want to do is make sure that we switch our agent primitives over to a different layer that doesn't have those unsimulated Vellum shapes in it. And so this is something that could definitely present a bit of a problem if you had a lot of geometry variations. In our case, we just have one skin shape. So all we need to do is use an agent edit SOP to switch all of the agents over to our default layer, because there's just the one skin layer. So we already easily know what layer they should be switched to. But if you had a lot of different geometry variations, it could be kind of tricky to figure out what layer the agents should be switched over to get rid of those Vellum shape bindings. But once we've done that, then we can finally merge it with our simulated geometry and then play back our results as usual. So then let's jump over to the Houdini 19 example, which is using the new layering workflow. So here, the basic idea with the setup is still pretty similar. There's just going to be a few differences related to the layer and shape workflow. So here again, we're taking our initial agent primitive and using the agent unpack SOP to get the rest geometry, and then doing our Vellum setup exactly the same as we did before. So once we've done our Vellum setups, again, we're using the Vellum pack SOP to get both the constraint geometry and the normal simulation geometry just in one detail. And then in this case, we're going to be using agent layer 2.0 to set up our shapes and layers. So what we're going to do here actually is just take our two Vellum pack outputs, and in this case, we're also going to turn on the name option on Vellum pack to assign a name for these shapes. So we can do this ahead of time rather than on the agent layer SOP. So here, for the one variation, I've just called it cape long, and then for the other one, I've called it cape short. So then on our merged geometry, we have our shape names already set. So then on agent layer 2.0, our shape name attribute is set to name. So we're, of course, importing those two shapes. And then I'm also using that workflow of setting the layer name attribute to be the same as the shape name. So we're getting one layer per shape. And so we have a layer for cape short, and then we have a layer for cape long as well. And so then, as before, the rest of the setup's the same. You finish setting up your agent definition and animation and so on. And then once you've gone ahead and populated your crowd, then you can use the crowd assign layer sop if you just want to add those vellum layers to particular agents. So in this case, we're just randomly selecting 80% of the agents and assigning them either the long or short cape. So in this case, it's a little bit easier to work with because we don't have to create new combinations or new layers that combine the vellum shapes with particular skin shapes. We can just create those combinations on the fly by using the crowd assign layer sop. So there's a little bit less manual work if we have various base shapes that these cloth shapes might be associated with. And again, we could also be doing this after the simulation too. So I can actually just rewire this. So we could do our crowd simulation as normal, and then afterwards decide, okay, we actually want to assign some cloth to particular agents. And then the agent Vellum unpack sop now has a few new options to take advantage of this. So the agent layer selection option works a little bit differently. It's rather than checking whether the agent's single current layer matches this pattern, is checking whether any of the agent's assigned layers match the pattern. So here we're going to simulate any agents where one of the layers assigned to it is a cape layer. And then, just as before, previously we were selecting based on the shape name, which shapes were going to be simulated vellum shapes versus collision geometry. But now there's also an option to select by layer. So we can say any layer named, whatever pattern we want to use is going to contain shapes that are going to be simulated. So this lets you use the workflow of having multiple layers assigned to an agent to decide which shapes or which layers are going to contain the vellum shapes versus the collision shapes. But as before, you can also do this based on shape names if you want to as well. And then the pre-roll settings are exactly the same as before. So we can still run our simulation and get the cached results. And then one other change is now how we deal with getting the agent primitives back to layers that don't have any of the unsimulated vellum shapes so that we can merge them with the final simulated results. So one of the nice things here is that because we're using multiple layers to assign the vellum shapes, getting rid of the vellum shapes just means getting rid of that layer. So we can just edit the layers that are assigned to the agents. So what we could do here is if we take our simulated crowd, we could, for example, use a crowd assign layers sop and set this to remove any layers that match the vellum layers. So we could just set that to cape star. Oops. And now we've removed those vellum layers from the agents, and then we could just merge those directly with the simulated results. And so as a convenience, the agent Vellum unpack sop can do this for you. So if you are selecting based on the vellum shapes based on a layer, this new fourth output here will contain the agent primitives, but with those layers removed from the agent's list of current layers. So now you can just take this fourth output directly and then merge it with the simulated results. So that wraps up the section on the updated geometry variation workflow in Houdini 19. Thanks for watching.